All right, this video is going to try to shine some light on things that I really haven't emphasized so far in the course. And these are really non-productive equilibria. Now that sounds pretty fancy, but it's not very fancy. This is just a fact that just because we write one thing on the page doesn't mean the reaction doesn't try other things. Okay, this is kind of inefficiency in chemistry, but it's the reactions exploring what's going on. So one thing I'll point out is in the aldol condensation, we will take a carbonyl, some ketone, and we'll react it with a base like sodium hydroxide or sodium alkoxide, maybe methoxide, ethoxide. And what we emphasize is that we will get deprotonation of our ketone at the alpha carbon. And you know what? That does happen. Absolutely it happens. But other things can happen as well. So we know that sodium hydroxide, it's electron rich. And because it's electron rich, it's basic. Anything that's electron rich, however, is potentially nucleophilic. So something that we never showed, but it absolutely occurs, is the fact that hydroxide can attack a carbonyl. And that happens. What do we get when we attack this carbonyl? Well, anytime you attack a carbonyl, you get a tetrahedral intermediate. Now, as it turns out, this O- is not so stable, and what it says is, hey, hydroxide, you just gave me an O-. Get your tail out of here, and I want to go back to the carbonyl. This is a reversible process. So hydroxide can certainly attack the carbonyl, but there's nothing that can happen to this tetrahedral intermediate, and so the process just goes in reverse. This is a non-productive equilibrium. We don't need to talk about this equilibrium to account for our product, but certainly that happens. I'll show another example of a process that occurs that I've sort of ignored. When we do an aldol condensation, we form a beta hydroxyketone like this one. And we said, okay, getting towards the end of this reaction, sodium hydroxide is going to deprotonate this alpha carbon to make this enolate. And, you know, that totally happens. And ultimately, this enolate kicks out that hydroxy, and we form our alpha-beta unsaturated ketone. But how does our base, sodium hydroxide, know not to deprotonate on this side of the molecule? That's also an alpha hydrogen. Well, as it turns out, it doesn't. And sodium hydroxide will indeed deprotonate at that position. I said sodium hydroxide, whatever our base is, I've written hydroxide, so it'll deprotonate that alpha carbon, and we will make a new enolate over here. As it turns out, this enolate can't do much. So what happens? The enolate says, this isn't so fun. I'd just soon get protonated again. And so it bumps into a water molecule and will pick the proton back up. This is a non-productive equilibrium. It doesn't explain our products, but it certainly is something that happens in the reaction. You engage in non-productive equilibria all the time. So do I. When I go in our kitchen, sometimes I'll say, I really want something to eat. Now I'll open up the refrigerator, and, you know, there's all kinds of stuff in the refrigerator, cheese or something. I don't want a piece of cheese. I want like chips. I want something good. So then I go to the pantry. Well, my wife won't let us have any chips in the house. So what do? I'll go back to the refrigerator. So, you know, here's all this I don't go straight to the thing I want. I got to explore the situation a little bit. And then I decide, that cheese that I saw, that doesn't sound so bad. So I'll have a piece of cheese. So these are non-productive equilibria. People do it. Chemical reactions do it as well. So don't be too bothered by the fact that there are other things that occur. But however, we need to make sure when we design reactions that the other things that can occur don't lead to our final products. Otherwise, we're going to get side products. But often many things can occur and they're not going to affect the fact that this is still a good reaction and it forms primarily one product.